Yeah, so the others already did a bit of an introduction. I started on this project with my master thesis, as Victor said. He was my advisor there. And then we wrote a paper about it and keep developing it ever since. So I will talk a little bit. In this talk, I will not talk about anything Tableau or Hyper related, just that it's clear the LeanStore project is separate. It's what I'm doing in my PhD. It's a different code base and also more to leaning towards a transactional system, not an analytical system such as Hyper. Okay, so a bit of context here. We believe there's currently a third wave of database architecture happening or necessary in the modern world, so to say. The first world is one that has all these components here that you probably all heard of during your studies, your undergraduate, how a typical classical database system looks like. So you have a buffer manager, you have some logging component, you have a latch manager, or no, sorry, not a latch manager, you have a log manager, and you have some latching to do. And this is the architecture that was pioneered in the 80s. IBM mostly wrote a lot of papers about their DB2 system, and that is basically the ground base that everybody still teach today. But then there was this famous paper in 2008 that made a breakdown of the costs of a typical TPCC transaction. TPCC is a transactional benchmark for database systems. I think most people are familiar with it. And what they showed in their study is that most of the work spent in a database is not actually done on useful stuff. So not actually processing the transaction itself, like inserting the tuple or doing some calculations, but overhead work that is necessary for maintenance tasks. So for example, the biggest chunk here is the buffer manager, as you can see, with over 30%. And then you have, as I said, logging, latching, and locking as other big contributors. So starting in the 2010 years, there was this big wave of what I think, or we think, is the second wave of database architecture, and that are these in-memory systems. And I think we all know them. Hyper is one of the famous pioneers there, but also other systems. And what those systems did is they got rid of a lot of those components at the cost of only being able to execute workloads that fit into memory. So you store your tuple data not on disk anymore, you store it in in-memory vectors, which simplifies a lot of stuff. For example, the buffer manager can be completely omitted and you don't have to spend that overhead work. A lot of those systems were also redesigned from the ground up to be more efficient on modern hardware. So multi-core scalability was big already in 2008. It was not big in the 80s. So those systems were more optimized to exploit multi-core CPUs. So in the end, those systems got much faster than traditional systems, multiple orders of magnitude in some cases. But the problem, as is obvious, is in a pure in-memory system, like it is defined in a very strict sense, all your data has to fit into memory. And another, Peter, can you perhaps mute yourself, please? Another fact that we all are aware of is that data sets are ever growing. So we have the era of big data. So despite huge main memory capacities of, let's say, multiple terabyte, it's easy to order a 6 terabyte main memory machine off the shelf today. Data sets are even larger than that, and they keep growing. And with this trend, we looked at how we can design a system that is as fast as in-memory systems, but doesn't have this restriction of only being limited to a data set that fits into memory. And this name is not official. That's our term for it, we would like to call these systems, or the lower layers of those systems, high performance storage engines. So storage layers or frameworks, projects that have some way of managing data sets larger than memory, but when you access them, when you work on this data, still being efficient. And on this slide, there are a few examples for those systems. So there's, of course, our own LeanStore project, which started with a paper at ICDE in 2018. There is the relatively new Umbra project by Thomas Neumann, which effectively, as you might know, Thomas Neumann is also my PhD advisor at TUM, and Victor also works closely with him. So Umbra's buffer manager or storage manager has a lot of features pioneered by LeanStore. And there are other systems. This managing non-volatile memory looked at NVM mostly and tried to integrate that into the storage hierarchy as well with a lightweight buffer manager. And there's this feeder system and another one. And what is LeanStore? What is the difference to a classical buffer manager? And that makes it fast and scalable on new hardware, on modern hardware. And there are three main points that were our contributions in the original LeanStore paper. And that is pointer swizzling. It uses scalable synchronization primitives in the buffer manager itself that upper layers can build upon. And it has a new efficient page replacement strategy that is, while still effective, it is lightweight and cheap to maintain. Much cheaper than a traditional LRU queue in a normal buffer manager, for example. So let me explain it a bit in more detail how it looks on the technical side. So this is a classical buffer manager design that you see here. You have some global hash table that stores frames, buffer frames for each page that is currently loaded in the system. So those are only the database pages that are currently loaded in memory, not all of them that reside on disk. And in this frame, most often there's also the latch for this page is also contained here, and some other metadata information. And you have a couple of those, and then on the pages itself, of course you have also a pointer to the page data. And these pages traditionally used to be 4 kilobyte, or in other systems 16 kilobyte, but it's the usual size of those. And on those pages themselves, you store page IDs. And when you want to do a lookup in a B tree, for example, you somehow know the root of your B tree. It's on page 1, for example. Then you load page 1 via the fix primitive in the buffer manager. It loads the page from disk, creates this frame here. And then on this page, you find other page IDs that you have to follow that are in your usual B tree structure. And then you take one of those page IDs and do a lookup again in the buffer manager. So for each page lookup, you have to go through this chain here. You have to do a hash table lookup, latch the page, have the indirection of the page frame to get to the actual page data, and so on. And that is what mostly contributes to those 34% that I showed earlier. So what is LeanStore doing here? LeanStore is using the technique of pointer swizzling, which has been pioneered in the context of object relational databases also longer ago. I think Professor Alfons Kemper is one who wrote papers about this topic as well. And pointer swizzling is a technique where you have the same 8-byte that you use for an in-memory pointer can also hold an on-disk page ID. So it's basically a union data structure. And there's one bit, the uppermost bit, for example, to discriminate which one it is. And our idea was that for hot pages that are accessed often, you don't want to have this overhead of going through the buffer manager doing the expensive hash table lookup all the time. So instead of storing a page ID, you directly store a virtual memory pointer on the page. So when you dereference a hot page, you just do a virtual pointer lookup, and then you're basically as effective as an in-memory system that uses an in-memory B tree. And then you can follow that chain, and all is good. When you hit a page that was not accessed yet or that is cold, that still contains the original on-disk page ID. And then you have some component in your system. In ours, it's called the I/O manager. And then you ask it to load that page. And then you exchange that that page 3 here with the in-memory pointer to that page over here. And that gets rid of a lot of the overhead of the usual lookup operations. What you also see here is a cooling stage on the lower left. And that is our implementation for the page replacement strategy. So usually on every page access in a traditional buffer manager, when you call this fix operation and you do the hash table lookup, you also update an LRU queue, which an update of a list. That list is in memory, but still compared to in-memory systems that don't have to do this, it's expensive. And you see it in your perf traces. So we switched the idea on its head, so to say. It's not that on each page access, which happens, page accesses happen all the time, you update this information, but instead you have some background process that sometimes just says statistically, with some probability, a certain page becomes hot. So that some cold. So it looks at hot pages and it chooses one randomly and switches it to the cooling state and puts it into a queue. So the difference now is you have in this queue only the cooling pages, and those cooling pages make up a low percentage, let's say 10% of your buffer pool. So you don't have to pay this eviction strategy update overhead on 90% of the page accesses, but only on the 10% of the cooling pages. And then pages, there's some process that, or some thread that puts pages into this queue, and the oldest pages, as they age in that queue, so to say. That's how we think of it. And as soon as they get too old, it means nobody has accessed the page and they get evicted to disk. So if it's a dirty page, it has to be written out. If it's a clean page, it can just be thrown away. And then on the lower right, you have this I/O manager that I talked about. It also needs a separate data structure, another hash table that has entries for every page that is currently being loaded. You need that because in your system, when you have multiple transaction threads that are doing transactions, 2 of them could access the same page at the same time, and you have to synchronize them, so that not 2 of those load the same page in different buffer slots, for example, but that the page gets only loaded once. One point, it's more efficient to only do the I/O once, and also for correctness, it's necessary. One point that I omitted so far is with this page replacement strategy, what we did is, if a page gets accessed that is currently in the cooling stage, then it's taken out of there. So you have this pages that line up in this list, and they age, they move to the right. And if a transaction needs one of those pages, it picks them out. So this list always contains pages that are not accessed, and as soon as they are old enough, they get evicted. This is, again, an overview of the different states a page can be in our system. So you have completely cold pages only residing on SSD or on disk, in this example, on secondary storage. When you load them, you also swizzle the pointer. We call it this union that I talked about earlier, we call it the swip, can either hold a pointer or page ID. You swizzle that swip, and then it contains an in-memory pointer. When you move a page from the hot state to the cooling state, you unswizzle the swip, you replace it again with its page ID, put it in this queue, and then it's in the cooling stage. When it gets accessed again, as I just said, it's swizzled again. If it's not accessed, it's evicted. This was all the state of our first paper, LeanStore. And then in our recent work, we also we thought about it again, how it should work and how we can tweak it even more, because that process worked. But to be honest, for the out-of-memory case, you had to tweak a lot of parameters. It was not very robust and stable, and we redesigned it. And in the code, the changes were perhaps not that significant, but from our perspective, how we look at it, how we think of it, it was quite a new redesign. And we now think of it as you always want to keep your buffer pool in an equilibrium. So you have these different states, and pages flow between those states at certain rates. For example, if your data set is larger than memory, then you always, and you do a scan, for example, you read pages in at a certain rate because you have to load them from secondary storage. So in this example, you always read pages with 900 pages per second. And in the equilibrium, your buffer pool is full. So in order to read a page from disk, you need a free buffer frame or buffer slot. So that is why this arrow comes from the free area here. And we always keep a low percentage of pages in free, just so that when a worker thread requests a page, it doesn't have to pay the price of the latency to wait, or perhaps even to have to look up in some data structures and do the operation itself. It should always be in a state where there are some free pages that it can just take. So this is taking a page out of this free stage is a very cheap operation. I think it's just I think it's a very cheap spin lock that you have to acquire, and then you can take the page out. The pages themselves, also to avoid memory allocations, this is an implementation detail, but I think those are interesting, so I will we'll spread them across the talk a bit. The pages themselves have a next and pointer embedded in their buffer frame. So not in the content area of the page, but in the metadata area. So you always have the chance to link pages into a single linked list, which just avoids that you have to allocate another data structure for the linked list that only holds that information. It's all just there. Okay, so when worker threads need to read new pages from disk, they take them out of this pool, and this constitutes this stream up here. But then a worker thread could also request a page that is currently in the cooling stage, or in the cool stage, and then it has to swizzle pages at another rate. And we hope that this rate is small, right? Because it would be super inefficient if we have to unswizzle pages and then immediately take them out again. So with this random strategy, we benchmarked it, and it fared quite well. We compared it, it's in the paper, we compared it to a few other strategies, and it was competitive with them. So yeah, we have this other rate here of pages that need to be swizzled in again. And then all this is done by the white arrows, which represent the worker threads. And then everything that is not strictly necessary, that doesn't have to be strictly necessarily done by the worker threads, is done by another thread, a background thread, which we call the page provider. And that is now, its job is to unswizzle pages at a certain rate. And we can now exactly say what this rate needs to be, because it needs to match that rate, the rate in which pages are going into the hot state, when we think of it that we want to keep the percentages at level. And from this cooling stage, some of the pages might have been dirty, so the page provider has to persist them, and also some can, and then, right, so everything that has not been swizzled back needs to be evicted then at some point to make the page free. We also experimented with having separate threads for these three different tasks, unswizzle, evict, and persist. But that didn't pay off in the end. The synchronization between those is so tight, they're so tightly coupled, that it paid off to have just one thread to do it all. Right. And with that, I want to show some performance numbers that we had in the initial paper. And these support our claim that we were able to implement a lightweight buffer manager, LeanStore is the green bar here, that is which performance is on par with an in-memory B tree, which we implemented ourselves to avoid noise. The B tree implementations here are identical. It was all templated code. And in one case, the B tree just had an allocator that always returned pre-allocated free in-memory pages. And in the other case, it was our real LeanStore implementation. And as you see, the overhead was really little. Also, we were competitive with Silo, which is another existing in-memory system. And when you compare to the performance of a traditional disk-based buffer manager system like Berkeley DB, we are much faster than that. This here is single-threaded performance. Perhaps it's also interesting to look at the absolute numbers. So a lot of papers always talk about scale-up and stuff, but we think single-threaded performance is important as well, because it's your baseline. You can scale very well, but if your single-threaded performance is 10 transactions per second, then that doesn't give you really much in practice. So we were able to achieve around 60,000 transactions per second on an Intel Core i9, I think it was. Right. Looking at scalability, you can see that our buffer manager, LeanStore here, scales almost as well. I think it scales as well. This is misleading in the graphic because there's a small difference here at the baseline with one thread. It actually scales as well as the in-memory B tree, but the absolute difference just grows with a growing number of threads. We also implemented LeanStore with a version that doesn't do the optimistic latching, which I will talk about in a second. And you can see here that with a few threads, it still works, but once you go up to a higher number of threads, that approach doesn't work very well. It basically has too much overhead in the latching of the B tree pages all the time. And Berkeley DB, as you can see, it was one of my initial points. Traditional disk-based systems were not optimized for multi-core from the ground up, so they don't scale at all, I would say. They scale a little bit, but then fall back to their baseline performance. Right. So what we also looked at is system behavior over time, which it's easy to get a data point where your system reached 60,000 transactions in 1 second, but then fluctuated a lot and decreased or so. We were always interested in looking how robust it is and how well it performs over a longer period of time. So here in this example, we started with the in-memory buffer pool almost full, and then let the system run for a while. And one thing you have to know here is that for TPCC, your data set grows all the time. TPCC is just ever growing. So when you started with such high transaction rates, like we have here over 600,000, then after a few seconds, it outgrows your memory and is basically an out-of-memory workload. And what we want to show here is that once we go out of memory, our system performance decreases, but it's only gradual. So there's no sharp drop. As you see in the blue line, it just degrades gracefully. The blue line here is again our in-memory B tree. And what we did here is we relied on swapping, because at the time there were some papers that said, yeah, you can implement a system like an in-memory system and everything is fine. You just rely on the swapping behavior of your operating system and it will work. And we were suspicious of that. And this experiment also shows that it's not very robust and also performance drops a lot. You get very unpredictable behavior together with a few other functional problems. And Berkeley DB is very stable. that's one plus point here. Its performance is super robust once you go out of memory. You don't see any difference basically, and that is behavior we have also seen with Postgres. At some point, it doesn't matter how much memory you give Postgres, it doesn't drop its performance. It just stays on a flat line, no matter if your working set fits into memory or not. And that is with a little asterisk. Of course, all these experiments had logging disabled, so there were no fsyncs involved here. And WiredTiger is, so to say, the spiritual successor of Berkeley DB. It's newer. It's Margot Seltzer, who developed Berkeley DB, is also part of the team that develops WiredTiger, I believe. And as you can see here, its performance, it's much faster than the original Berkeley DB, but it also has some problems. Once the workload goes out of memory, performance gets a bit unpredictable. You will see that again later for our logging experiments. There we saw the same. Here is a startup time. I think that's also interesting. Note that the y-axis is logarithmic, and this really shows one of the points we had in the paper, that these fast NVMe SSDs that are now commodity, but back then when we wrote the paper were quite new. So PCI Express attached SSDs are quite a game changer, because they are not limited by the slow SATA interface anymore, and can achieve by now with PCI Express 4, I think, something like 4 GB per second read bandwidth. And here you see that when we start up our system cold, so the buffer manager is empty, whole data set resides on disk, and then we start TPCC, it only takes a few seconds until, with a PCI Express attached as a fast SSD, until the system warmed its cache. Every page, all the hot pages, frequently accessed pages are in RAM again, and then system performance is high. With another SSD, it takes over 30 seconds until the state is reached. And with a classical hard disk drive, you see that it basically never finishes to get at high transaction rates. It always stays around, as long as we let the experiment run, it stayed around like 10 transactions per second compared to 600,000 transactions per second. And this this just highlights that a point I want to make. I don't say that those systems in the 80s, they were badly designed. They were just designed for the hardware that was available back then, and they made a lot of sense. They also had optimizations that were necessary for hard disks that we completely omitted. For example, we don't care about at all that we optimize for sequential read or write I/O, because SSDs offer random access. But for hard disks, this was, of course, necessary in those systems. Yeah, so this just shows that all the three main features, pointer swizzling, the eviction strategy, on the optimistic latching, which I will talk about in a second, are important. And you see that for the single-threaded case, it's just about cutting overhead away here to get to those 67,000 transactions per second. But for the multi-threaded case, the optimistic latching is basically all that matters, or is the most important part to get to those performance numbers. You need the other two as well, but this is really what gets you there. Also, you see the eviction strategy here is more important. That is because the classical eviction strategy, of course, increases the time you hold latches, or it just involves more synchronization than ours. We designed it carefully so that this background thread picks random pages, and on average, a random page that you pick is not currently used by any of your worker threads, because you might have millions of pages in your buffer pool, but only like 100 threads or so. So it just cannot be that statistically that a random page you pick is at the moment locked or latched. Okay, then this page here, it's titled From Epochs to Optimistic Lock Coupling. this is an important learning that we had, because when we initially wrote the LeanStore code and implemented the synchronization, especially of the B tree, it was very complicated. And we thought of it, okay, optimistic latching. Perhaps I explain now what optimistic latching is in its base version. It is that you don't physically write to memory to acquire a latch when you only want read access to some data. And how it works is you have a version, for example, a 64-bit integer, and that acts as your latch, your memory position of the latch. And when you want to read something, you read first the latch, you get your number, then you read the actual content of the page. For example, you do the binary search to find the successor page. But then, since you have never acquired a real latch, a writer might have made the data dirty, right, in the meantime. So after you have done your read operation, you have to read the version counter again and compare if the pre-version and the post-version are the same. If they're not the same, there has been some writer in between, and you have to restart your operation. So all the code paths in LeanStore are designed in a way that almost all low-level operations are restartable. That is one requirement to make it work. A writer, before it starts to write, it sets the highest bit in this 64-bit integer. So it definitely has changed the version before it actually touched the content and has overwritten it. And then after it is done with unlatching, it increases the version +1. And with 64 bits, you basically never have the case that this overflows in realistic scenarios. And if it would overflow, you could also implement solutions for that. I think, yeah, Thomas did that in his Umbra implementation, because Thomas is always concerned about having it correct in all corner cases. Okay, so now you have this primitive of an optimistic latch. But in a B tree, it's more complicated. A traditional B tree in a buffer managed system, also in in-memory systems, often does a technique called lock coupling. Or alternatives to that are B-linked trees, but lock coupling is one standard approach. And we thought we couldn't do that, because with these optimistic latches, we thought of them more like a lock-free data structure. And in lock-free data structures, you have one problem, and that is when you delete something, you cannot throw it away immediately. You have to keep it around in a waiting list and make sure that nobody reads that piece of data anymore, and only then can you get rid of it. A standard approach in that area, in this lock-free data structure area, is to use epoch management. And how that works is each worker thread, before it touches the data structure, it enters an epoch. That is shown here on the slide as well. So for example, thread 1 is in epoch 9 at the moment, thread 3 is in epoch 5. And then when the thread starts its work, it reads the global epoch. There's one global epoch that's always incrementing. It reads that into its local epoch field. So thread 3 in this example started earlier. Back then, the global epoch was still 5. It read it, and since then it kept it. So thread local epochs can lag behind arbitrarily behind the global epoch. And then when a thread puts a page into the cooling stage that you see on the left here, it attaches some additional information there, namely the epoch that it observed. And then there's some garbage collection mechanism, and that ensures that a page here only gets really evicted to disk only if no thread is in that epoch anymore. So that resembles those log-free epoch management approaches. But then one of Victor's other master students found out that all of this is unnecessary. So in this picture, I only showed little part of that code. It was super complicated code. It had a lot of dependencies. It was spread around the code base. And in my master thesis, I talk about all kinds of edge cases that can happen and that you have to think about when a B tree splits. It gets complicated. But then, as I said, one of Victor's master students found out, hey, it's much easier than that. We can just do something, we can just do log coupling with optimistic logs, and it works. And that increased our system robustness immensely. It made the code much easier to reason about. And how that works is you basically just copy the scheme of traditional log coupling. In traditional log coupling, you log node A, you access it, and then before you unlock node A, you first log node B to have this coupling effect. And you can do the same with optimistic log coupling. When you think of reading a version just and verifying a version just as the equivalent of acquiring the log. So you read a version of node A, you read a version of the other node B here, which is V7 in this example, and then before you access that node, you validate again that your version here in node A has stayed the same. And then you have optimistic log coupling. And one of the 4 papers that Nadia, I think, shared with you. No, sorry, that was another group. So one of the papers in our system talks about this. Perhaps this is a good point to show you the project website. So this is our LeanStore project website, and there we have at the moment 4 papers, and one of them talks about this log coupling in a little bit more detail. Right. With that, the initial LeanStore buffer manager part is over, and I would say before I continue, are there any questions so far?
I have some questions regarding the implementation you made, but I think I will leave that for the end maybe. I'm not sure how, because I kind of want to know what was your experience implementing this in Umbra. I don't know if you were involved in this.
I was not. I talked to Thomas a bit, but I have no access to the Umbra code base that is separated.
I think I'll leave it for the.
Yeah, sure. As other questions regarding how it works, what's the reason behind it, or the benchmark results? If not, I would continue with logging, with the logging part.
Michael,
yeah,
I have a question about an image for the buffer pool where there were some this new design with the free space and the hot and cool space. Yeah, this one.
This here?
Yeah.
Okay.
Yeah. So I was wondering about the percentages here and the rates that exist here. These are indicative, or do they depend on the workload? How do you tune them?
We tried out different values and those worked well for us. That is the honest answer. We thought about them and they should be pretty robust in practice as well. But we haven't made a careful evaluation, so to say, which, so we didn't correlate which values would be best for which workload.
Okay. All right.
With the cooling stage, there's always this trade-off that you want to have it. You don't want to have it too small, because then pages don't stay long enough in there if it's too small, and they might get evicted despite being actually hot. Because with this random strategy, once sometimes you just hit a hot page, and you want the system to give it enough time to access it again before you would evict it.
All right.
And if it's too large, then the disadvantage is just that the stage has more overhead and it's more expensive to access pages in there, and you want to have most pages with this cheap access. That is the trade-off you have to do. And this 10%, 5%, something in that area turned out to be good in practice.
All right. Okay. Got it. Thanks.
Other question? Yeah.
If I may, very quick question. In the optimistic latches, how do you guarantee correctness when the version overflows?
So in our research prototype, we just don't. We ignore this problem. Theoretically, I think an overflow itself is not a problem, as long as you handle that you don't overflow into that highest bit that you use to mark it as write locked, for example. It just has to be guaranteed that your thread is not stuck long enough so that basically the 64-bit counter overflowed while during the first initial read, the pre-read, and the post-read, because then the data changed, but the thread would read the same version. And we don't, we ignore that problem in practice, because that would mean until that counter is overflowed, that thread would have been clocked for months or years, basically. The overflow itself is not a problem. It doesn't have to be ever increasing. You just need to make sure that if something changed, the pre and the post version don't match.
Yeah, well, the same issue, by the way, applies to Lean's own system. But anyway, I had a question for Victor. I didn't know the LeanStore GitHub page, exactly the DBIS page. And I saw the screenshots and the papers, but I missed one thing. I missed code in the GitHub.
Oh, yeah. So that's interesting, because there's multiple LeanStores, but none of them you will find on the internet. But maybe one day, maybe one day.
Yeah. So the problem is,
you already have the GitHub page. That's a good start, at least. Sorry.
No, it sounds familiar to me.
Nice. Yeah. Mike, Michael, you were going to say something.
Yeah, the problem for me is that I would like to share code, but I'm just simply not able to because of my Tableau affiliation. Everything I write belongs to Tableau or Salesforce now. The other implementation is in Umbra from Thomas, so you need to pick him if you want it. And the third one, yeah, as Victor said, is in Jena. So we have 3 implementations floating around right now.
No, yeah, well, I think the Jena implementation would be the most likely to be open source at some point then. I suppose, you know?
Yeah, I think so, yeah.
Okay.
Then I will continue with the logging part. So yeah, we considered, after that first LeanStore paper, we considered the buffer manager part solved. So we came back to this famous picture that I already showed, and another big chunk of work that you see here that's also interesting to look at is logging. So we looked into that topic again, and much like with buffer managers, there was the same series of events, I would say. Classical systems basically all used some form of alias, which Mohan wrote about in his famous paper about 91, 92, I think, and it's also the de facto standard. You read that everywhere. But there was this sentiment flowing around that alias is too slow. And yeah, there are some papers that even state this here. Alias cannot provide the bandwidth required in today's multi-core systems. So what most of those in-memory systems did is they, as with the buffer manager, they came up with some new lightweight form of logging. And the thing with that is most of those schemes were designed for in-memory systems as it makes sense, but that means they didn't have this page component, that a log entry contains a page ID, and yet that you have this physiological logging where you address a page physically, but then inside the page you replay the redo log record logically. They were just designed in a different way. So, and another point is alias has a set of nice features that ideally you want to have in your system. One of them is fuzzy checkpoints. You have this efficient recovery when there are repeated crashes, because it has these log compensation records. Also, it transparently manages index and space management recovery, since Arius is based on the page abstraction. And in the traditional database, all the space management data structures, all the indexes are also stored in buffer pages. That all works very nice together. And especially index recovery is something that's often overlooked. So the traditional in-memory approach would be, those systems of course have some option to spill your data out to disk and then shut your system down and restart it and read everything back. But they usually only have in-memory indexes, and those indexes are recreated when you read your data back after a restart. And index recreation can be costly. So when you read back a 1 terabyte database into main memory, you have to create indexes for those 1 terabyte of data. And those, there was a study that showed that in transactional systems, the size of the indexes can make up to half of the entire data size. So they might be as large as the data set themselves, because you have multiple indexes with different keys on the same data. Another thing is support for very large transactions. Also something in-memory systems don't need, because they cannot have transactions that are larger than memory, but disk-based systems can have. For example, when you rewrite a table, when you do an update x equals x plus 1 on a table that is larger than memory, then you have easily you get one of those large transactions. Yes. So what we wanted is the best of everything, of course. We wanted a fast system with little overhead, scalable, but which has all these nice features. And what we found, or what we came up with, is this logging in LeanStore approach that I will show you now. And it's based on scalable logging approach that was proposed by Wang and Johnson in 2014. And they already proposed it for systems that have non-volatile memory available. And we also support transactions, low latency commits with this persistent memory, because we thought a lot about it, and we somehow were opposed to the idea of group commit, which a lot of systems do to get high transaction rates in in-memory systems. But we wanted to achieve single synchronous transaction commit with low latency and still achieve those high transaction rates. Our system supports fuzzy checkpointing, has low instruction overhead, because we want to build everything as efficiently as possible. And a cool property is that we guarantee a bounded recovery time. And of course, since our indexes also live on pages, bounded recovery time, including index recovery. Right, so how does it look like? Here's an overview of the system. And on the right, you see worker threads that are working on transactions. And we implement kind of classical Arius style log records. So the log records do look like very much like Arius log records. And we also use a traditional write-ahead log-based system, because that just fits very naturally into our existing buffer manager and everything. And also, we think that, yeah, it's battle proven, it works, and it was kind of obvious to follow that idea. So we have multiple chunks. Let's say each chunk is 100 megabytes, where we can write in log records. And there's always a current chunk. And each worker has its own list of chunks. So these whole area of this list of chunks and also this val writer, they are all separate per worker thread. So a worker thread can insert log records very easily. There's always this persistent memory chunk that is mapped into the address space. So we use the DAX access method to have very low overhead. And basically your interface, your programming API is, you have some special mmap call that you do on your persistent memory device, and then it looks like virtual memory. And so we have those memory allocations here. We write log records into there until log chunk becomes full. And then it is moved into a list of full chunks. And from there on, it is taken care of asynchronously by a background while writer thread. Again, so that our worker threads are blocked as little as possible by work that they don't have to do. It is not absolutely necessary to do. Right, and a while writer then stages those chunks to SSD, because one property of our system is that we want to have this low latency commit that persistent memory enables, but actually persistent memory is still very expensive, and we don't need it for anything else than this low latency commit. So if your log grows larger, we actually want to offload that to a cheaper storage medium like SSD, and the bandwidth that the SSDs provide, as I showed before, is more than sufficient to absorb that large amounts of log. So once a chunk is written out, it gets into this free list again, and then the worker thread can pick it up there again. So each worker thread writes its own separate log records. So if you're a bit familiar with classical arrays, you see immediately that there's no single increasing LSN log sequence number anymore. So we have to find a solution for that. And that we luckily could rely on what was done by the Scalable logging paper by Wang and Johnson. So they came up with a global sequence number, and that borrows ideas from vector clocks. So, vector clocks are a generalization of the Lamport clock in distributed systems. So in our system, each log, each transaction, and each thread act like participants in a distributed system. And with those global sequence numbers that they proposed, that are proposed by Wang and Johnson, we can enforce a partial order that is still enough to guarantee correct recovery. So log entries that are separate don't have to be ordered anymore according to this GSN. They can have the same GSN if they are independent. Let me talk about a problem that was in this initial Wang and Johnson paper that we looked at, because how they solved it, they implemented a special version of group commit. They called it passive group commit. But as I said before, we were on the standpoint that we don't want to have group commit because it increases single transaction latency. It introduces some, again, some asynchronous component in your system. It makes the design more complicated. So we tried to get away with without those group commit flushes. By the way, should I explain group commit, or is everybody familiar with that?
Well, they should be, but who knows?
Okay, then just a little bit. So in a traditional system, when the transaction reports commit back to the client, this database system must ensure that the data is persisted. So if it crashes right after it has sent the commit back to the client, it must still make sure that the transaction is recoverable. So how the easiest way is, or the most straightforward way, which is not very performant, is before you send the commit back to the client, you flush all log records to a secondary storage device. Because even traditional systems used to write them in memory first into a memory queue, and then they flushed this memory segment to disk, made sure it is persisted on disk, so calling fdata sync or fsync primitives in the OS, and then they could report commit back to the client as soon as the write-ahead log is synchronized to disk. Problem with that is fsync is about the most expensive operation you can think of. Even with today's modern SSDs, it got a lot better, of course, but it's still slow. With a classical hard disk, it's in the order of milliseconds. So you can only do a few, no, I think even more. Anyway, you can only do like 100 of those or 1,000 of those per second. Even on those SSDs, it's better, but it's not perfect. And that limits your transaction rate, basically, if you do it in that naive way, to 1,000 transactions per second, because you cannot get more fsyncs to the device. So what a lot of systems did is with group commit, a transaction doesn't report immediately back to the client on its own, but it puts all its data into a group commit queue, and the thread continues processing other stuff, probably a new transaction. And then from time to time, all these transactions that are conceptually done, that just need to be committed, so that the user already issued the commit, they're all in this group commit queue, and then they are flushed at once, because you can flush larger amounts of data in one fsync, and then all those are flushed at once, and then all clients are notified that their transactions committed. So that is a solution that a lot of systems do. But of course, since transactions cannot commit immediately, but have to wait in this group commit queue, you introduce additional latency for the clients. And we especially thought about the scenario that, well, in a benchmark, it's easy to issue 1 million independent transactions that can run, and you always saturate your server, your database server. But in a real system, it might be that a client issues a transaction, wait for its commit, and then depending on that commit, it issues another transaction. So you have those chains. We didn't find hard evidence for that, unfortunately, yet, that these appear in practice a lot. But I think if your system is capable of handling each transaction immediately, if committing it immediately, and have this low latency, you would support that use case much better, of course. Okay, that was group commit. Back to remote log flushes and what they are. Okay, so we have, let's start easy. We have 2 transactions, TX1, TX2, and transaction 1 inserts a data item A on page A and then commits. Transaction B updates a data item on page B, then inserts another data item, also commits. So when you look at this, there is no logical dependence between those 2 transactions, and they don't even have to touch the same physical page. So in theory, they could proceed completely independent of each other. With a classical Aries log implementation, however, you have a single log. So each log record that gets written needs to acquire a latch on this single log data structure. So they are all synchronized, and you basically sequentialize the operations. With this distributed logging by Wang and Johnson, you can write now log records independently. So these update and this insert record can be written because each record thread has its own log. But in order to ensure correct recovery, also in the presence of persistent memory, even there, you have to flush all remote logs as soon as you commit your own transaction. And that is because your log records might depend on changes done by other transactions that, and those transactions might have not committed yet. So imagine your log records support increment to log increments, so you only log a +1. And let's say you have those dependencies, and there's a +1 here, and then your transaction finds it on the page. You also do a +1 and then commit. If that +1 log entry gets lost somehow because it is not flushed yet to persistent storage, then you have a problem because you depend on it. But in this case, there is no dependence. Still, this logging scheme here has these remote flushes because it cannot differentiate it. And what we thought about, if I explain it like that, it seems like a very obvious and simple idea. Perhaps it is. We have a lightweight tracking mechanism, so a transaction can see if those remote lock flushes are necessary or not. So what we do is for each lock record that gets written, we check if there are unflushed, potentially unflushed records in other locks, and if there aren't, we have a flag in each transaction that says, yeah, you can go ahead. You only have to flush your own lock, none of the other locks. Why is this important? Because even in non-volatile memory, we saw, and I think I have some numbers for that in the evaluation, that these remote lock flushes become prohibitively expensive. Because somehow when you access that other lock here, you have to acquire at least a spin lock, and it's an O of N operation, right? When you want to support systems with 100 cores or so, or 200 cores, this gets more and more expensive. And also, you have to do a flush. While it is a flush in persistent memory, it's still a flush of the cache, and that has some costs, and you have to do that for every other partition. So with our approach, which we call remote flush avoidance, we can get rid of most of those remote lock flushes, and only, it's a heuristic, but in practice, only those transactions that really have a dependency on other lock records, only those need to flush other locks. We don't make a distinction there which other locks it has to flush. We just say, okay, you are in the loser bucket, so to say, you have to flush all other locks because it didn't pay off to do this fine granular tracking. That would have been probably too expensive. Okay, that is the logging part, how we manage to scale that and make that work. By the way, I talked about overhead before. We didn't see, with a careful implementation of areas, when you log it into persistent memory, we didn't see that overhead was too bad. It's visible. Unfortunately, we didn't have time to optimize it too much. It was still like a TPCC transaction took something like 50,000 instructions, and 10,000 instructions on the worker thread were required on top of that for logging. So it is something like 20%, but as long as it's scalable, it didn't seem prohibitively expensive as claimed earlier. Nadia, do I still have time? I don't know if we have to adhere to some.
Yeah, I think we're a little bit past 2, so maybe wrap it up and to have time for some questions.
Yeah. Okay. So here, this part would have explained how the checkpointing algorithm works in practice. The gist of it here is that we have some incremental checkpointing that gets rid of most of the burst I/O that traditional systems see. Postgres is one example there. We also saw it in Via Tiger. And those write I/O bursts are really bad for a system. They are not easy to handle. So we got rid of those and smoothly write out pages all the time. And then we did some benchmarks on that. We were lucky enough to get a cool machine at university that has real Intel Optane persistent memory. So we could do real experiments there. And this looks much like the scaling graph I showed you earlier. You see here that our system performs very well. We were able on that machine, which is a bit larger than the machine in the former experiments, we were able to get to over 800,000 TPCC transactions per second. And we also implemented a group commit competitor, and we were even very close to that one. And this point I still want to make, just a few seconds. We again looked at system behavior over time, and after a lot of tuning of the implementation, we were able, the text here is a bit crippled. ours is the green line here, we were able to get to a state where this page provisioner that I showed you earlier removed everything or as much as possible off to that background page provisioner, and it was able to keep the buffer pool in its equilibrium. So when the system runs out of memory here, at this point in time, so the x-axis is the time axis here, you don't see an observable drop in performance, or perhaps a very small one here. And we didn't expect that ourselves, because we expected something like in the earlier graph that I showed you, that you have this smooth performance degradation. But it turned out that if you tweak your system and get rid of every contention point and every overhead, then you don't even need to have that. And that was a very cool observation here, that we were able to run over 800,000 TPCC transactions in the out-of-memory case. Okay, some more experiments, some numbers on latency, again, some overhead numbers, how much, some dissection of how much the logging overhead cost, and that is it, basically. Thank you. Sorry for that I went over time.
All right, thanks a lot, Michael. So
okay. I see a lot of hands there.
Yeah, it's our virtual applause.
I thought you have questions. I wanted to keep calling you.
Okay, but are there any questions?
I have a question.
You can go first.
Okay, so great engineering talk. But you're also working in industry. That's also good. So you have a good perspective on actually the actual need of actually the functionality you were describing. So can you enlighten me? Where do I have the need in the real world for actually a system which handles 1 million TPCC transactions per second? And if so, how many are there at all in the world?
Yeah, I have multiple thoughts on that. One is, I think if you have a system that can use the hardware as efficiently and provide classical asset guarantees, then you might just use it for stuff for which you have otherwise fallen back to a system that doesn't provide them. I think about sensor data ingestion, for example. You usually wouldn't use a transactional system for that. Now you can. Of course, I don't.
CERN. You cannot support CERN with this rate.
You mean because CERN has even much higher input rates? Yeah. Okay, that's a point. Then we need to improve on that. But there might be use cases where you just, if you have a system that offers those guarantees and your transaction rate falls into this range, then you might use it. The other thing is, as I learned in industry, when you have a research prototype that achieves these many transactions in a perfect setup, then you can divide it by a factor of 4 or 10 or so. And that is the number customers will see in practice, or perhaps they will see even less. So I think it's important to lay that foundation, that theoretical foundation of what is achievable, and implement those primitives. And then you put it in the whole system and implement every corner case, every error message, everything. It will get slower anyway. So you might as well have a good base where you start from.
Okay, second question. You probably know the paper Retrospection of a Database System of 1980 by Michael Stonebreaker.
No, I have to.
Well, that's at least something you have to read for your thesis, because if I would be in your committee, I would recall that one. The retrospection of the database, one of the big questions and one of the big messages out of the early stage of Ingress was that if you're building a database system, try to do the work of the operating system. And what you're describing is actually all the things which you would ideally expect from a good operating system. So that brings me then to the next question. If that's the case, then you have to make explicit where you deviate from the operating system or the trends in operating systems. And it may be as simple as actually, well, how worse can it be or get when I rely on memory mapped files? Because pointer switching and memory mapped files addressed by offsets are identical in technique. So for the thesis, I would look for a comparison. How good are you compared to trends in operating systems? What could they learn from us? What could we learn from the current evolution in that area? But Peter wants to answer, I think.
Thank you. I wrote that down. I will take it as input, definitely. Thanks.
I'm not sure if I want to answer, but well, previously we did see that you know, you can rely on memory mapped files, but you will not get optimal performance. I mean, at least in the past, it used to be the case that you would have to use this asynchronous I/O libraries.
Indeed, and you can predict. So you can gain if you can predict what is your access pattern, because then the lower end systems can deal with it, and predict in terms of what you need, how long you need it.
Now memory mapped files actually do play a role in this current implementation, because it happens to be the high performance interface to non-volatile persistent memories. So it's a bit yeah, different. Maybe Victor can chime in on this one.
Yeah, so this is a very interesting discussion. So in a theoretical world, actually, what you'd want to build is you want to integrate these LeanStore things into the operating system, because actually in a transactional system, using mmap is actually very difficult to actually get logging and recovery correct, right? Because you can get evicted any point in time, and you have no control over that, right? So now you could build something like areas with a couple of additional hooks into the operating systems. Then you can build these things, right? But then you don't run on standard kernels, right? So these entire discussions kind of very interesting and very subtle. So I don't think there is a simple answer. And my general thing is that it is actually in particular in the transactional space, and if you're pragmatic and you want your software in production, then you have to use like standard operating systems, right? And then you cannot change them, and then the implementation that you have right now in Linux and so on. I mean, Michael was showing those graphs. If you rely on swapping, it's terrible. And the faster the SSDs become, and if you have several of those, then it becomes really terrible. So because nowadays these SSD that you have now, they have dozens of gigabytes per of I/O bandwidth.
Yes, but he countered his own argument, because his last remark was customers actually are happy if they see a 4 to 10-fold below the theoretical optimum. So in that respect, the thrashing may not be a problem from the customer point of view.
I don't know. I mean, I don't buy that. I think if you give people performance, they will find use cases to waste it. I think this is what Michael said. But it's still useful to give it to them so that they can transform that performance into easier development or into just throwing more data into that. I don't see that argument. It's true that the original scenario of TPCC, of course, that's bonkers, right? Nobody does 1 million like orders per second, right? But a workload where you actually have that many reads and write small reads and write updates, they do exist, right? They are not the kind of like really merchandising kind of operation.
So make it explicit. So in terms like actually the underpinning of these theoretical experiments, try to identify concrete use cases.
And maybe gaming actually.
Yeah.
Maybe gaming. I'm not sure.
Yeah, I know. Yes,
there were some papers from on that. I think they have pretty high rates. Yeah.
I mean, another way of looking at it is everybody has performance problems in database. That everybody uses databases who has performance problems. This is the reason why we're all like, in my experience, right? So people always find a way to waste whatever performance you give them, right? And usually they transform it into making things easier for them, right? And having a less well-designed schema and so on, right? So in a way, our service is to give as much as possible, and then people will find a way to waste it. And
yes, because they often don't write correct SQL queries.
Exactly, that's one reason.
So we're helping stupid people to do more stupid things quicker.
Yes, and that's great, right? Because people are, this is I think what we're doing if we're realistic.
I had another question for Michael. So this is kind of leveraging, modern storage trends, persistent memories and then high bandwidth SSDs, multiple of them. But very many people are moving their data to the cloud. And in the cloud, you may in fact have also some NVMe, although maybe not in extreme amounts as you can have them if you build your system yourself. But these SSDs are not reliable. They are ephemeral storage, and they will be empty if you shut down your machine. So the real storage in the cloud is in things like S3 and Azure Blob Store. So given that is, whether you like it or not, the modern operating environment of let's say database servers, I think I can claim that because there's maybe embedded stuff, but that's on the laptop, but database servers in the cloud. So how does all this work translate to actually this current environment?
I have a very good answer for that. I'm very happy about that because that will be the focus of my next paper. We thought about the same thing, and I can subscribe what you just said. We think in the same direction. If it doesn't run on commodity cloud offerings, nobody will use it in practice in the future anymore. I pulled up the screen here just to make your point again.
Two small letters. I'm looking at my telephone. Sorry.
Yeah. So as you said, a lot of EC2 instances in AWS now offer large amounts of local instance storage, fast NVMe drives, but as you said, they're volatile. So exactly the direction, as you said, we were thinking about some design where you leverage that to gain huge transaction rates, but your persistence layer in the end will be something like S3.
Well, not in the end, but you will have to continuously log to it or something. Otherwise, it's not persistent.
Yep.
Yeah.
It's interesting that Amazon does not have yet instances with persistent memory, or not last time I looked. Google Cloud said they announced it, but I didn't see that you can get them yet. So
but
persistent memory is tricky.
Yeah, it's tricky, but it will have the same problem as SSDs. It will be ephemeral.
Yep. No, I don't have the technical answer yet, but we're looking into that area.
I think we're slightly over time. But that's Nantya to say, actually.
Yeah.
What were you going to say, Victor?
No, I was saying thank you for that question, because I was also trying to basically pitch that project to Michael, but I think he's on board. So.
Okay.
So maybe have a last question by Mark, since he, I think he wanted to ask something.
Yeah, sure. So kind of a minor question. Of course, the main focus of your work is on OLTP workloads. Our group is doing mostly OLAP stuff like analytics. Do you think for in analytical database systems that don't really care about transactions, is LeanStore still applicable, or is memory mapping just good enough? Or should you still use LeanStore? What is your opinion there?
You see what Thomas did with Umbra. This is basically an analytical system where he implemented the buffer manager. I would say definitely. MMAP gets you far, but we also see Hyper still uses mmap as its primary storage backend, right, or access method for database files, and it's not without problems. So if we would have some very lightweight buffer manager in there, that would get rid of some of those problems.
All right. Now, of course, I'm asking this because I am also considering this question, and I was heading in the direction of a lightweight buffer manager. Particularly, also one reason for us is that mmap, when you access a random entry, a random memory address, it can trigger a page load from disk. And if that disk is gone or so, it will just send a bus signal. Yep. And for an embedded application, that is particularly problematic because you can't really install like signal handlers in an embedded application. And particularly if you load from like a network FS, then this is very, you can just get random bus signals, which you don't really want as in an embedded scenario, basically. Like, yeah, you'll just bring down the host. So this exactly. is why we were looking towards not going the mmap route, basically. So it's nice to see that enforced, basically. So thank you for that.
Yeah, and I think, yeah, I mean, getting actually many laptops have fast NVMe now, so yeah.
And by the way,
well,
if I may add to that, if you think about multiple SSDs, so I mean, this is maybe not the InductDB use case, but we actually did those experiments that if you sequentially read through mmap through an SSD, so not in the non-cached case, you get to about 2 GB per second, right? But the thing is, these SSDs are much faster now. You can have several of those. So the operating system is actually not fast enough. Maybe they will fix it at some point, but so I think also even for the OLAP case, in ideal case, you want your own buffer manager, but you might not need it to be as fancy basically as LeanStore is doing. For instance, you probably won't be doing, I wouldn't do pointer swizzling. If I'm in an OLAP only system, I would not do pointer swizzling. It makes things easier. And so that would be my.
Yeah, it was also my initial thoughts were that LeanStore is a bit too complex. Even it's not so complex, but it's a bit too.
It doesn't buy you that much, that complexity.
Yeah, you don't really need all of that. Well, indeed, good point about the multiple SSDs. It's very interesting. Thank you.
Yeah, I pulled up a picture here. This is a card that you can buy. It's not that expensive. You can put four M2 SSDs on there, put it in your normal PCI Express 16 slot, and you get a system now on a modern machine that for under $1,000 or so, you get a system with 15 gigabytes or more read bandwidth. That's really impressive, and that's you get in the area of memory bandwidth there, which is around 100 gigabyte per second, depending on your server. So it's really game changer.
I see. Very cool.
Especially if you combine it with compression. Yeah. Then it may actually be enough to run queries from.
All right, so any more questions? Michael, maybe you can share an email with us if someone wants to get in touch with you to ask a question later.
Sure, I can send you that. I can also say it here on the talk. It's mhaubenschild@tableau.com, but I will send it to you in text.
Okay, all right, yeah. Okay, so yeah, Peter, did you want to?
Well, okay. No, I just wanted to thank you and thank, of course, Michael and also the visitors from Jena.
Mm-hmm.
So, yeah.
Yeah, of course. Yeah, thanks a lot, Michael, for accepting our invitation and for the great talk.
Thank you.
All right, so yeah, the CWI people see you on Monday, I guess.
Yeah.